Hello and welcome back. In the previous lectures, we were looking at solution thermodynamics and how we can model various thermodynamic properties for a mixture of chemical species. Along that discussion, we introduced the concept of ideal solution, and we said to account for non-ideality, we use what are known as activity coefficients, one of the ways to account for non-ideality, that is. And these activity coefficients, if you recall, we have defined it as gamma I for species I is the ratio of fugacity of that species in the solution or the mixture over the fugacity if that solution were ideal. So it is ratio of Fi hat over Fi hat for an ideal solution, of an ideal solution, right? And it turns out, because of this definition and the relationship between the fugacities of species in the mixture to the chemical potential or the partial molar Gibbs free energy, this ratio will actually yield the relation that the logarithm of the activity coefficient is partial molar excess Gibbs free energy over RT for that particular species, G I bar E over RT. Moreover, because of the summability relation, the total excess Gibbs free energy of the solution, GE over RT, is sigma xi GI bar E over RT, and because GI bar E over RT is related to the activity coefficient, this equation will become sigma xi ln gamma I. In addition to this, we have also derived the criteria for phase equilibrium using the equality of chemical potentials and hence the fugacities, and we expressed fugacities in terms of fugacity coefficients and the activity coefficient. And the final relation we had yesterday was for the liquid phase, the fugacity of species in the mixture is xi gamma I pi sat, where pi sat is the vapor pressure at the temperature we are interested in, times phi sat, that is the fugacity coefficient for the pure species at the temperature of interest, and this will be equal to the fugacity of the vapor phase, which is yi times p, the partial pressure, multiplied by the fugacity of species I, fugacity coefficient for species I in the vapor, phi hat, right? On the left hand side, we have fugacity of the liquid phase. On the right hand side, I have fugacity of the vapor phase. Of course, this relation ignores the Poynting correction factor for the liquid phase, and if the total pressure of the mixture is not too far away from the vapor pressure pi sat, then this is a fair approximation, right? Let me re-emphasize each of these terms here. This is the liquid phase mole fraction, and yi is the vapor phase mole fraction. Total pressure, and this is the fugacity coefficient for species I in the vapor mixture. So if I were to write the functionalities for the vapor phase, this will be a function of the temperature T, the pressure P, as well as the mole fraction yi. I can use any suitable equation of state, be it virial equation of state or a cubic equation of state, to obtain the vapor phase fugacity. Now for the liquid phase, I have xi, which is the liquid phase mole fraction. Let's see, pi sat is the vapor pressure of pure liquid, in this case I, at temperature T. It will be only the function of temperature because it's pure liquid, so pi sat is only the function of temperature. It's the vapor pressure of that species I, and phi sat is the fugacity coefficient at the saturation conditions, and so it will be a function of the temperature and the corresponding vapor pressure, which is Pi sat, but this is still for pure species I alone. It's not in the mixture. So it is independent of that composition Xi. And gamma I is the activity coefficient, as in case of all other thermodynamic properties. This activity coefficient, because it is related to partial molar Gibbs free energy, in strict sense it will be a function of the temperature, the pressure, as well as the liquid phase composition X. But in real life, the effect of pressure is somewhat weak. It doesn't affect the liquid phase activity coefficients that much, so usually we ignore that functionality of pressure. But nevertheless, thermodynamically, it is a function of the temperature, pressure, as well as the liquid phase mole fraction. So this is the phase equilibrium relation we have looked at yesterday. Now, one can simplify this phase equilibrium relation by making certain assumptions. It turns out that if the vapor phase is ideal, well, let me write what we had in the previous slide. Yi p phi hat is xi gamma I pi sat times phi at the saturation condition. Now, if the vapor phase is ideal gas-like, then phi hat will be 1, phi sat will also be equal to 1, and I can write it, that equation reduces to YIP is xi gamma I pi sat. And in addition to this, if we have an ideal solution, recall for an ideal solution, gamma I will be Fi hat over Fi hat for the ideal solution. And because it's an ideal solution in itself, both of them will be Fi hat ideal, or that ratio will turn out to be 1, which means YIP is going to be equal to xi pi sat. This is for an ideal solution and the vapor phase behaving as an ideal gas. This equation at the end is more commonly known as Raoult's law. Of course, we know the underlying assumptions to be able to use Raoult's law, right? So in any of these equations we have seen here, all of them relate on one side the fugacity of the liquid phase to the fugacity of the vapor phase on the other side. Depending on the conditions we are at, the temperature, the pressure conditions we are at, we can use one or the other form of these equations. Of course, neglecting the activity coefficients or assuming the solution to be ideal also requires knowledge of the chemical species, and if those chemical species do form an ideal solution or an ideal mixture or not. So with that, what we will look at next is how I can use the vapor-liquid equilibrium information to calculate the excess Gibbs free energy. If you recall, one of the equations we have written for ideal gas-like behavior for phase equilibrium is xi gamma I pi sat. For now, for sake of simplicity, let us assume that this equation is valid. The solution is not ideal. We have an activity coefficient that is not equal to unity. If I have this relation, what I can do is rewrite this equation to get the activity coefficient in terms of the mole fractions of the vapor and the liquid phases and the vapor pressure of the species I. So activity coefficient is going to be related to them via this equation. We can perform an experiment like we discussed yesterday, a vapor-liquid equilibrium experiment, obtain the composition of the liquid phase, obtain the composition of the vapor phase, the total pressure, and hence calculate the activity coefficient at equilibrium conditions for each of the species I. If I perform this at various mole fractions, then I get activity coefficient as a function of the mole fraction xi. Once I have the activity coefficient, recall that the excess Gibbs free energy GE by RT is sigma xi ln gamma I. So once I have the activity coefficients, I can go back and calculate the excess Gibbs free energy for that particular mixture. The excess Gibbs free energy or the activity coefficients indicate that the solution is ideal, then things are simpler. If the solution is not ideal, then we need to build a model that represents the behavior of that particular solution. When we say a model, if you recall, we said activity coefficients are functions, and GE by RT for that matter, are functions of temperature, pressure, and the mole fraction X. The functionality on pressure is weak, so what I'm looking at is a model for activity coefficients in terms of temperature and X, or at constant temperature. What we are looking for is a model for activity coefficient in terms of the mole fraction X that is applicable at that particular temperature or pressure of interest. Once the temperature changes, then that model of course will change. So we can do experiments at constant temperature and pressure conditions, obtain how GE by RT or the activity coefficients behave as a function of composition, and then try to model such a behavior, right? Now, before we talk about the models, let us first look at broad behavior of these activity coefficients, especially as we have done in the other cases at the ends of the especially as we have done in the other cases when the composition approaches pure component limits. So, for sake of discussion, let us consider a binary mixture. So I have x1, I have x2, and then GE by RT is going to be x1 ln gamma 1 plus x2 ln gamma 2. As we approach the pure component limit, let us consider a mixture which is like this, and most of it is component 1, except I have a very small amount of component 2. At such limit, x1 going to 1, which means x2 is going to 0. At this limit of pure component 1, what we will see is that the mixture is fairly ideal because most of it is made up of only one component, and the excess Gibbs free energy GE by RT will be equal to 0. Also, if you want to look at the partial molar Gibbs free energy, right, I will drop the color code for now. G1E by RT will be equal to G1 bar by RT minus G1 bar in an ideal solution over RT. And in both cases, because I am approaching the pure component limit, both these terms, G1 bar as well as G1 bar ideal, will equal that of the pure component at this limit, right? Pure component values, which is G1 by RT minus G1 by RT. So that will be 0. So at the pure component limit, the total Gibbs free energy as well as the partial molar Gibbs free energy for 1 will be equal to 0. If this is 0, what this means is ln gamma 1, which is G1 bar E over RT equals 0, or gamma 1 equals 1. It's approaching an ideal solution behavior. So the activity coefficient for that species will approach 1. Now, what happens to the activity coefficient of the other species 2 at this particular limit? Now, recall that at this particular limit, we said that it is the limit of pure component 1 or infinitely dilute 2. 2 is in such a small quantity that we call it as infinitely dilute. At this infinite dilution limit for 2, what happens to its activity coefficient is what I'm interested in. What I'll do is I will resort to the Gibbs-Duhem equation, which reads a sigma xi dmi bar equals 0 at constant temperature and pressure. This is the Gibbs-Duhem equation. I will use this equation and I'll use the partial molar Gibbs free energy G I bar E in this particular equation. So this will read x1 d G1 bar E over RT plus x2 d G2 bar E over RT. I'm just using it for a binary solution, will equal 0. And recall that G1 bar E over RT is ln gamma 1. So this is x1 d ln gamma 1 plus x2 d ln gamma 2 will be equal to 0 at constant temperature and pressure. This is Gibbs-Duhem equation written in terms of activity coefficients 1 and 2. Now for this particular equation, let me rewrite that again. X1 d ln gamma 1 plus x2 d ln gamma 2 will equal 0 at constant temperature and pressure. Now at constant temperature and pressure, recall that we said activity coefficient will only be a function of composition. That's the only thing that's left. Temperature and pressure are anyway held constant. So that derivative then is taken with respect to the composition or the mole fraction. Let's take it with respect to mole fraction of species 1. It doesn't matter. It's a binary. We could equivalently take it with respect to mole fraction of component 2. But for now, let's say it is with respect to component 1. So this is the Gibbs-Duhem equation written in terms of activity coefficients in a binary mixture at constant temperature and pressure. Now, if you look at this equation, we said that at the limit x1 going to 1 and x2 going to 0, which is the infinite dilution limit for 2, the first term gamma 1 will go to 1, which means dln gamma 1, it will go to a constant value. So dln gamma 1 over dx1 will be 0, which means the first term drops out. And if that drops out, then the limit of x1 going to 1 and x2 going to 0 for the second term, which is x2 dln gamma 2 over dx1 will be equal to 0. Now, as x2 goes to 0, if the product of x2 multiplied with another term, in this case dln gamma 2 by dx1, should equal 0, then it automatically means that the second term here should be finite. Because x2 is going to 0 and the product is going to 0, the only way that happens is if the second term in this product will be a finite quantity, right? And that finite quantity then is what we're going to call it as gamma to infinity. So limit of x1 going to 1 and x2 going to 0, right? ln gamma 2 will be what we call as ln gamma 2 infinity, or gamma 2 will be what we call as gamma 2 infinity. This is infinite dilution activity coefficient for species 2, right? So gamma 2 will be gamma 2 infinity, or the infinite dilution activity coefficient for species 2. So at the pure component limit, so let's summarize then what we just did. All we did was we have used Gibbs-Duhem equation to obtain this. At the infinite, at the pure component limit, x1 going to 1, x2 going to 0, gamma 1 will be 1. And at the same limit, x1 going to 1, x2 going to 0, gamma 2 will be at infinite dilution condition, so its activity coefficient will be gamma 2 infinity. Similarly, at the other limit of x2 going to 1, x1 going to 0, gamma 1 will be at its infinite dilution condition, so it will be gamma 1 infinity. And at the same limit, x2 going to 1, x1 going to 0, gamma 2 will be pure component 2, so gamma 2 will be equal to 1. So this is the summary of how the activity coefficients behave in a binary system as we approach the pure component limits. Now that we know how they behave at the ends of the phase diagram, right, and to make sure that this behavior holds, it turns out that the limit of x1 going to 0 GE by RT x1 x2 will be equal to ln gamma 1 infinity, and limit of x2 going to 0 GE by RT x1, x2 will be equal to ln gamma 2 infinity, right? And we can show this based on our previous discussion. So what we usually do is to be able to model the behavior of activity coefficients 1 and 2 with respect to composition, we rather model the behavior of the excess Gibbs free energy because it incorporates both gamma 1 and gamma 2, and then take its partial derivative with respect to N1 or N2 to get the partial molar Gibbs free energies or the activity coefficients. In general, in a power series type of expansion, the way we represent GE by RT x1, x2 is a function of power series either in x1 or x2 in a binary mixture, it doesn't matter, plus so on. We can reduce it into a more mathematically convenient form as GE by RT x1 x2 is A plus B x1 minus x2 plus C x1 minus x2, well, let's use capital letters, whole square plus so on. These expansions for GE by RT over x1, x2 are known as Redlich-Kister expansions. These are expansions for the excess Gibbs free energy at a given temperature and pressure. So it is only function of the mole fraction. Now, out of these Redlich-Kister expansions, then depending on our requirement, we choose the first term, 2 terms, 3 terms, etc. We can choose as many terms as we want out of this power series expansion. So let's start with the simplest scenario where GE by RT, let me demonstrate how we calculate the activity coefficients based on this model. GE by RT x1, x2 is only A. Every other term after B, including B, is 0. If this is the case, then GE by RT x1, x2 will simply be A, or GE by RT will be A x1, x2. Now, if I want to find the activity coefficients from this particular model, then what we do is take the derivative of, or we want to obtain G1 bar E and G2 bar E. So what I will do is I'll multiply it with N, the total number of moles in the binary mixture. And what I get on this side is N1, N2 over N. Recall that when we take the partial derivatives to obtain the partial molar properties, we want to convert all the mole fractions into number of moles of each of the species. So when I multiply it with 1, N, x1 will change to N1, but x2 will remain as such, so I am rewriting it as N2 by N. Of course, remember that N is N1 plus N2, and derivative of N with respect to N1 is going to be hence 1. Now, with that in mind, what I will do is I'll take the derivative of NGE over RT with respect to N1 at constant temperature, pressure, and N2. If I do that, what I will get on this side is A, let us say it is written only for a particular temperature and pressure. So A is A, and N2 is constant. Derivative of N1 over N is N minus N1 divided by N square. And if we simplify this, this is A x2, and that will be 1 minus x1. So that will be A x2 squared, right? So the quantity on the left-hand side, if you recognize, is partial molar Gibbs free energy, excess partial molar Gibbs free energy for component 1, which we'll call, which is related to the activity coefficient as ln gamma 1. So ln gamma 1 using this model will be A x2 square. We can go through a similar exercise and also show that ln gamma 2 will be A x1 square. So this is the simplest model we get using the Redlich-Kister expansions for excess Gibbs free energy. Now if I ask a question, what is gamma 1 infinity? Then we can use this model and say that gamma 1 infinity is nothing but the limit of x1 going to 0 for gamma 1, and as x1 goes to 0, x2 will go to 1, so a times 1 squared would be simply a. So in this model, gamma 1 infinity will be a, and if we actually write gamma 2 infinity, this will also equal a. So for this particular model, gamma 1 infinity equals gamma 2 infinity will be equal to a. So the infinite dilution activity coefficients are what this term a represents in this particular model. Rather, this is logarithm of infinite dilution activity coefficients to be more specific, but then that is what it is. Now let's look at a model which is slightly complicated than this, and we call this as Margulies equation. What we'll do is we'll take the Redlich-Kister expansion up to two terms, a plus b x1 minus x2, and we'll drop all the other terms from c onwards in the infinite series. If that happens, we'll readjust this a little bit. This will be a x1 plus x2 plus b x1 minus x2. x1 plus x2 anyway is 1, so it doesn't matter. And then I can write it as a plus b times x1 plus a minus b times x2, right? And we'll give a name to this a plus b quantity. We'll call it as a21 x1 plus a12 x2. So I can rewrite the model equation, Redlich-Kister expansion, containing two terms in this fashion. GE by RT x1 x2 will be a21 x1 plus a12 x2. Now we want to get the activity coefficient for this particular model. So what we need to do is first get the partial molar quantities out of GE by RT. And GE by RT will be a21 x1 square x2 plus a12 x2 squared x1, right? Well, this is still GE by RT, not NGE by RT. Now if I make it NGE by RT, then this will be a21 n1 squared n2 over n squared plus a12 n2 squared n1 over n squared. Notice that I'm multiplying only with one n, and I have a cubic in the composition on the right hand side, so I still need to multiply and divide with n squared so that everything is converted in terms of n, and we don't leave any compositions in there. Now once we have it in this form, I can calculate the partial molar enthalpy. Now once we have it in this form, I can take the derivative of this quantity with respect to n1 and obtain G1 bar E by RT. So the derivative of NGE by RT with respect to n1 at P, T and n2 will be equal to a21 times n2 is constant, and I have n1 square whose derivative will be 2n1 times n squared minus 2n n1 squared over n to the power 4. And for the second term, it will be a12, n2 square is constant, n squared minus 2n n1 over n to the power 4, right? So this will be 2a21 x2 multiplied with x1 minus x1 squared plus a12 x2 squared multiplied with 1 minus 2x1. So this will be 2a21 x1 x2 squared plus a12 x2 squared multiplied with x2 minus x1, right? So that will be derivative of NGE by RT with respect to N1. I can simplify this and rewrite it in a more convenient form. It turns out that G1 bar E by RT will be equal to ln gamma 1, and the simplified form of that will be x2 squared A12 plus 2 times A21 minus A12 times x1. And similarly, if I take the derivative with respect to N2 at constant N1, I will get ln gamma 2, which will be x1 squared A21 plus 2 times A12 minus A21 times x2. This is ln gamma 2. Now, if I ask a question, what will be gamma 1 infinity? If we want to know what the infinite dilution activity coefficients are, we simply need to take the limit as x1 approaches 0, ln gamma 1 will give us ln gamma 1 infinity, and that quantity will be simply A12. And similarly, if we take the limit as x2 approaches 0 for ln gamma 2, we get ln gamma 2 infinity, and that quantity as x2 approaches 0, notice that x1 will approach 1. This term drops out and we are left with A21. So as you can see, in this case, the infinite dilution activity coefficients for species 1 and 2 are not same, they are different. One of them is A12, the other one is A21. So once I have a model for GE over RT, then I can use that model and obtain the activity coefficients from that information. The other popular model is what is known as Van Laar model. And in this particular model, what we do is we write a power series for inverse of GE by RT x1, x2. And that looks like A prime plus B prime x1 minus x2. We can rewrite this as A prime plus B prime x1 plus A prime minus B prime x2, just like we did it in the Margulies equation case. And when we do that, what we have is A21 prime x1 plus 1 by A12 prime x2. So this is the model equation we start with, and then we take partial molar derivatives and do the regular exercise, and finally what we get is an expression for ln gamma 1 as A12 prime 1 plus A12 prime x1 over A21 prime x2 to the power negative 2, and ln gamma 2 will be A21 prime 1 plus A21 prime x2 by A12 prime x1, also raised to the power negative 2. And if I want to know what the infinite dilution activity coefficients are, ln gamma 1 infinity will be the limit of x1 going to 0 ln gamma 1, and that quantity, if I put x1 to be 0 and x2 to be 1 in this particular equation, what I get is simply A12 prime. And similarly, ln gamma 2 infinity will be the limit as x2 going to 0, x1 going to 1, ln gamma 2, and if I put the limits in this particular equation, what I will get is A21 prime. So again, using the model, I can calculate the activity coefficients and what will be the activity coefficients at the infinite dilution limits. Now, all these models we have looked at so far are based on power series expansion. They have very little theoretical basis behind them. The next set of models that have been developed for activity coefficients or excess Gibbs free energies are based on the concept of local composition. What local composition essentially means is that the liquids are not completely randomly mixed, but on a molecular level, there is an influence of the short range interactions between the molecules, and the molecular orientation itself is not completely random. It is based on what its neighboring molecule or how its neighboring molecule is oriented. Based on these concepts, several models have been developed. Some of the popular ones include what are known as Wilson's equation, the non-random two-liquid theory model or NRTL model, the universal quasi-chemical approach, which is known as UNIQUAC model, and finally the UNIQUAC model, and finally a functional group type of approach known as the UNIFAC model. Now, the approach behind calculating activity coefficients from the excess Gibbs free energy models in all these now, the approach behind calculating the activity coefficients using any of the models is essentially the same as we have looked at in the previous scenarios when we used the Redlich-Kister type of expansions. The only difference in using these models is there is some theoretical basis behind them, and we can sort of relate the model parameters to the physics behind the interactions between molecules of various types. So, for example, in case of an RTL equation, I'll just illustrate one of them for sake of an example. The NRTL equation, in case of NRTL equation, GE by RT x1 x2 is given as and using this model for excess Gibbs free energy, one can derive the relation for activity coefficient 1 as x1 plus x2 G21 and the parameters notice that G12 here within the model equation has nothing to do with the Gibbs free energy, and this G12 and G21 are written in terms of alpha and tau 12. And tau 21, and tau 12 itself is written as a function of temperature. B12 and temperature, B12 is a parameter that is independent of temperature. So, in addition to representing the composition dependency, because the parameters tau 12 and tau 21